Good afternoon, ladies and gentlemen. My name is Midshipman Robert Novak, First Class. I'm a student here at the United States Merchant Marine Academy. And with you today, I'd like to share the construction and testing of the suction wing for the generation of high lift forces. This is a project that I've been undertaking for the past 3 years with the help of Professor Perez, and I believe this project could further the future of vessel sustainability. So a brief introduction into suction wing technology. It essentially acts as a unique way to generate high lift forces for maritime vessels, and its purpose is for the wide-scale use of ocean-going wind in order to reduce ocean-going vessel fuel consumption by anywhere between 15 to 35%, and air emissions as well. Our testing essentially began with some preliminary tests of a suction wing device model and tested the high lift force generation when wind was applied onto the wing and suction was applied through the wing. And our model wing displayed preliminary results that showed a marked increase in aerodynamic lift force when suction was applied as compared to without suction. So some background into the device and the concept. So essentially, the suction wing is based on a 1900s concept known as boundary layer suction. And boundary layer suction essentially operates by allowing for a hollow chamber within an airfoil. And as you can see in the bottom right picture, suction slots for suction to be pulled through uh, the wing itself and to the outside wind. And as wind is applied over the front of the wing, the suction is able to pull the boundary layer closer to the wing itself, and the wing is able to create more lift as a result of this. And the implementation and research into this device was marked by Jacques Cousteau, who researched the efficiency and the applicability of installing these devices onto vessels, such as you can see on the top right there, the Alcyone, constructed in 1985. The research done by them was very remarkable and essentially acted as a founding pillar for our project, actually, and as a comparison basis for a lot of our research. And the use of suction within these airfoils and wings, um, I wanted to mention, also allows for thicker airfoils to be used, as the thicker airfoils are able to create higher coefficients of lift, which, although are subject to separation, the higher angle of attack allows for them to give higher coefficients of lift. But because of the suction being pulled through, they are less prone to greater to as much separation to compare to without suction. So allowing for the suction allows for that higher angle of attack, the thicker airfoil, and the much larger lift coefficients. So through this, the size of the mast and the sails on the vessels can be reduced. And as a result, of course, the objective is to reduce fuel consumption and air emissions. So the operating principle of these airfoils, as you can see on the left there, is at some variable angle, marked in the blue there, those airfoils, as some wind direction is applied to the wing, thrust and a lift force and a drag force will be as a result created on the vessel, and the resultant thrust will help push the vessel forward and help reduce those fuel consumptions. So on the right there, my hypothesis has been that over time, as these auxiliary wind propulsion devices have evolved, their maximum lift coefficients possible have increased, and it's been projected that the Cousteau turbo sail, as it's also named, is capable of a maximum lift coefficient of about six, but the goal of this research is to determine whether this is true whether it's less or whether greater lift coefficients are possible. So, short visual analysis of what boundary layer suction looks like for the suction wing. It can be seen here as flows applied at the same angle of attack for an airfoil, that the left airfoil is being put under boundary layer suction while the right is not. So you can see that the suction is able to pull the boundary layer back down closer to the wing, and that as the air is flowing over the wing, it stays closer to the wing, and greater lift is able to come out of this. And when no suction is applied inside the wing, that the air on the outside just flows over and begins to separate and mix, and less lift is able to be produced as a result. So our cart modeling process began with a large 3D printed hollow model of an airfoil with slits on the upper camber on the trailing edge of the device of the upper camber. And this was handed down from a previous midshipman to myself, and I worked on this device by initially installing the device on a rotating disc and installing the rotating disc onto a fixed body for the airfoil in order to test the directional forces of the airfoil. And I did this by assembling a cart to which to install the rotating disc on, so that I could change the angle of attack and measure the resultant thrust and lift, the lift and drag forces resulting from it. So I did this by applying an adhesive to the bottom of the airfoil and applying it to that rotating disc, which were marked at 10-degree intervals for testing. So as you can see in the pictures here, the blue airfoil is our testing device, and it's been applied to a rotating disc, and that rotating disc is moved whenever various angles of attack are necessary, and the cart will remain in a certain direction whether it's measuring drag or lift. So the cart, as you can see, has wheels that are meant to move to or away from a measuring force gauge, which is used to determine the magnitude of the lift and the drag developed. So modeling the suction to the wing was also another process that we undertook, and this underwent a number of different steps, in that at the bottom of the cart, a PVC elbow piece had to be installed in order to direct the flow of air directly from the hollow chamber inside the airfoil down to the bottom of the cart and out of it. So this was drilled through and passed through, and from there, a series of flexible rubber hosing, or a coil of flexible rubber hosing, was inserted to the PVC pieces, and it was passed through the elbow piece and into a venturi tube. And the venturi tube was a device used in the series of suction, and as essentially as an aid for measuring and also increasing the pressure and decreasing pressure in the throat and increasing velocity as the suction is pulled from the suction source, and the difference can be measured inside a man-made manometer that we also constructed. And this was made by using a long series of thin tubing that had one side lodged into the throat of the venturi tube and the other side located at the entrance. And we were able to measure a number of different variables with this in our calculations, primarily volumetric flow rate and air velocity, which helped determine our output coefficients. After the venturi tube, we were able to construct a flexible silicone nozzle, which was taped and clamped to the end of the venturi tube and fixed onto the suction device. We initially began with a shop vacuum in order to pull suction through, but we determined that there was a low airflow rate due to the head losses in the system, and not enough suction was able to produce any remarkable results during testing with this low suction. So we, instead of using the handheld vacuum, which would have been resoldered to a pulse width modulator and a power supply, we actually opted for a larger 5 horsepower shop vacuum at with a constant power source, as this proved to have provided enough suction. So imaged here, as you can see in the top left, is the Venturi tube that was used. The suction was pulled from the left side and through the Venturi tube and passed into the right side, which led to the shop vacuum. And on top were a number of holes that could have been used for testing, and a majority of them were plugged, except for the hole leading to uh, throat of the Venturi tube and the entrance of the Venturi tube. And this was used in conjunction with the manometer, as discussed before, in order to measure the pressure differential with the uh, with water, and the height difference of the water was able to be used in conjunction with calculations like Bernoulli's equation in order to determine the airflow rate that we had through the suction that was passing through the airfoil, or suction that was passing through the suction device and through the hollow chamber inside the airfoil. And in order to relate that to how the wind speed over the air was relating to that and the kind of lift and drag that we were getting as a result. So they all kind of were incorporated together in our calculations. And on the right side, in the bottom right, is our shop vacuum in connection to our Venturi tube, and how our initial design setup was put together. This was very preliminary, but our outside model from this had evolved into something a bit larger, which, as you can see here in the middle, evolved into a large um, fan that was used in the on the suction side of the fan in order to draw an even airflow rate through a constructed model wind tunnel for the cart in order to help steady out the airflow through the over the device. And it also helped reduce any kind of fluctuations in air velocity and any kind of error that we may have inside the tunnel and around the wing. And it also provided for greater airflow speeds with this. So our setup can also be seen on the right here. We have our force gauge linked to the back of the device, to the back of the cart, directly measuring the force imparted onto the force gauge. And here can be seen a measurement of the drag of the wing, and the flexible hosing can be seen coming out of the underside of the cart, going into this Venturi tube and the suction device. And next to that can also be seen the anemometer. And the anemometer was also used in conjunction with the force gauge to not only measure the force that was being imparted from the wing, but the wind speed that was being pulled over the airfoil itself. So all of these variables were necessary in our calculations to determine the efficiency and applicability. Um, in the top left here, you can see our manometer setup as discussed before, used with the Venturi tube and the suction hosing being connected through and to our shop vacuum. And in the bottom left there was our testing setup. As you can see now is in the lift arrangement for a lift being measured through the um, wind tunnel, with an anemometer being with an anemometer probe being stuck through the wind tunnel, and with a small gap being used in order to prevent any leakages or losses out, but small, great enough such that the probe could be put in and out to measure the wind speed over the wing. So what did we observe from this? Well, during our testing, we were able to gather a variety of lift values and magnitudes over various wind speeds and at different angles of attack. And what we were able to determine is from our performance, our wing had an aspect ratio of 2.8. And this is compared to our reference for comparison for this report, which was the Cousteau report on windship propulsion, which in their testing used a 4.0 aspect ratio. And using their method for determining output and performance, there is a formula for determining that, and that's for the variable CQ. And that's essentially the volumetric flow rate of suction air pulled through the hollow chamber of the airfoil and through the venturi tube and the vacuum, divided by the product of the wing surface area, the thick airfoil being used, and the average wind speed of the air applied over the face of the airfoil during operation. And this came out as a dimensionless group that could be used as a base of comparison. And we arrived at a value of 0.0391, and we fell close to the values in conjunction with the Cousteau report. As you can see on the right side, they have their coefficients of lift and at various angles of attack through these different output coefficients of CQ. They were able to land on 0.036 and 0.05, where we landed somewhere between there at that 0.0391, with various lift coefficients being found at those different angle attacks. And we did as well. And this red line, as you can see here, was the was our measured results and how it compares. And we arrived at a relatively similar lift coefficients. But however, our CQ should have been slightly higher and between the 0.036 and 0.05, but our lift coefficients were slightly less than the black lines of the Cousteau report. And partially this can be attributed to the difference in Reynolds number used between our wing and their wing and the differences in our tests, and a various number of errors as well, and such as the equipment that we used. So continuing on with this, the lift and drag coefficient that we arrived upon could also be compared with the Cousteau report. And from their graph from before at those various output coefficients of CQ, they were able to arrive upon a indifferent relationship between the coefficient of lift and coefficient of induced drag that they were able to find at a specific effective aspect ratio. And our effective aspect ratio was again slightly less than theirs, as theirs was 8.0, ours was 5.6, but we were still able to use their chart as a basis of comparison because a majority of our drag during our testing could be attributed to induced drag. And as you can see again on the right, our red line is the results that we were able to find during our testing for coefficients of lift and coefficients of drag at various angles of attack. And the coefficient of drag is a bit greater than the ones that they had came upon at different coefficients of lift. So they were able to arrive upon greater lift coefficients as a result and lower coefficients of drag. And this is essentially due to the the increased Reynolds number as well as the increased aspect ratio. And this certainly could have resulted in errors in our results. However, this would be scaled up in the future in order to meet their Reynolds numbers and aspect ratio in order to determine exactly if our results were coming close. Overall, though, our results came very close to what they had met at the coefficient of lift, especially being right in the middle of what they had calculated and exactly what they had found. So, and again, as I mentioned before, the Reynolds number can essentially be attributed as a large error in the calculation, as we had a Reynolds number of just over 100,000, about 127,000. And their Reynolds number, as stated in their report, was somewhere between 300,000 and 500,000. So this is a magnitude of 3, 4, 5. And what we can say to this is to the left plot, the very top line is what can be attributed to the report's Reynolds number, and the line just under that is what we can assume to be our Reynolds number line. And at increasing angles of attack, the greater Reynolds number is more capable of producing higher lift coefficients and lower drag coefficients. And essentially, this can be attributed to the difference in size that we used and the difference in wind speed and all these different variables that differed in our experiments. So what were some limitations? Again, as I discussed before, the low Reynolds number that we had significantly impacted the kind of result, and the lift and drag coefficients that we were able to pull from our calculations significantly impacted what we were able to take from the report and how we were able to compare to it, and our just results as a whole. But we also had some minor limitations in terms of the equipment that we were using. We were using a pretty low quality force gauge that wasn't as precise as we had intended to use. It had fluctuated and oscillated in values pretty often. On top of that, we were using a slow motion movie in order to determine the exact values at specific moments in time of the wind speed and the force being generated. So this attributed to a great amount of guessing into what our exact value could have been, as it like to tend to steer away from the preset values when a certain force was preloaded upon the gauge. So it wasn't very exact in that manner. And the various equipment that we had used had varying levels of precision. Our anemometer, for one, went to 1 decimal place. Again, our force gauge was of low quality with varying oscillations, and in general, there wasn't a lot of accuracy in that. So some final acknowledgments. I'd like to again acknowledge Christopher Sue and Professor Garfalo for the 3D printing of the suction wing model that they had provided to us for this testing. Richard Crook as the lab director for enabling us to work in the mechanical engineering lab. Professor Nigro as the department head of the marine engineering here at USMMA for enabling our research and our for our project. And again, the report that I had based a lot of my research on was the Foundation Cousteau Winship Propulsion for from the Journal of Wind Engineering and Industrial Aerodynamics, 1980-1985, was where a number of these plots and these comparisons came from. So some final contact information. Again, you can contact me at my email or at my phone number if any questions arise. or any concerns or comments. But otherwise, I thank you all for joining me and watching my presentation. Um, I apologize that I'm not able to answer any questions virtually or and through this recording, but again, thank you and thank you all for having me here.